here intentionally, and I will say more today about this. And so the goal of this talk is to explain that if you want to so these connections are presented in the form of categorification. Usually this representation theory categorifies modules over this Lie algebra. And so the goal of this talk is that if you want to instead categorify representations of quantized enveloping algebras, so if you want to get connection with quantized enveloping algebra UQ of G, and then what you have to add here on this side is you want to add the word graded. And so that's sort of what I want to explain today. In some sense, this is the end of my talk because I sort of told you the main idea. But since I have more time, I will provide more details. And but this is really what I'm trying to sell. And and I'm being rather vague here. It's becoming more and more clear that this connection is very, very broad. For example, you can get any Lie algebra here at all in any integrable highest weight module, provided you consider appropriate Hecke algebra. And so you will hear more about it in Monica's talk. But today I will concentrate on my favorite case where really I just want to consider graded representation theory of this Hecke algebras and the most classical and sort of easy to consider situation. Hecke algebras of symmetric groups, or just the group algebras of symmetric groups. So modular representation theory of symmetric group here, or representation theory of the corresponding Hecke algebra. So today I want to consider symmetric groups and their Hecke algebras. On the left. And then it's known that there is a connection here with the basic representation over appropriate affine Lie algebra SL E hat. Okay, so and I want to concentrate on this first of all for pedagogical reasons, because already everything that almost everything interesting that's happening in these connections happens here. And there are still many interesting and open questions in this situation, so this is already interesting. On the other hand, another reason why I want to do this is because as you go to other modules or other types, it gets either more technical or conjectural, sometimes conjectural. So I really want to just talk about this situation, but I want to emphasize that this is a model for a much more broad connections. Okay, so since I'm going to talk about this, so let's fix the Dynkin diagram gamma, which will be affine type A. And the vertices are going to be labeled by integers modulo E. So this is the set of vertices, and I will assume that E is greater than or equal to, is an integer greater than or equal to 2. You could consider also the case where E is equal to 0. So that would correspond to A infinity type. And it also corresponds to representation theory of symmetric groups, say, in over fields of characteristic 0. And everything goes through in this connection, but somehow it gets a little bit trivial for us. And so we will concentrate on the interesting case of the root of unity or characteristic of positive characteristic case. And so together with this, I have all the usual Lie theoretic notation, which I might even forget to list. In particular, there will be simple roots, simple co-roots, fundamental dominant weights. Occasionally, I will need notation Q plus for non-negative linear combinations of simple roots. And finally, UQ of G will denote the corresponding quantized enveloping algebra given by the standard Chevalier generators EI, FI, and KI plus minus 1 for all I and I, subject to quantum cell relations. There is an action of this quantized enveloping algebra on the quantum Fock space, which is probably exactly what Arun was trying to write. And so this has a basis given by all partitions. So this is as a basis given by the set of all partitions P. And the formulas are exactly the ones or similar to the ones which Arun alluded to. And so on top of that, there is a natural projection pi defined essentially uniquely up to scalar onto V of lambda 0, the highest weight lambda 0 irreducible integrable module for this algebra. And if you take the empty partition, it's the weight vector of it's the highest weight vector of weight lambda 0. And this will be just generated by this empty partition vector. And then all the other irreducible components of the Fock space are different from lambda 0. So you can consider the projection which kills all of the wrong components and which acts on the right component. It's just the projection onto it. And then in here, we have the standard basis, which consists of lambdas. And the image of the standard basis elements will be denoted as lambda under this natural projection pi. So, of course, now it's not going to be a basis because this pi is not an isomorphism, but it's going to be some spanning set. So I will have this S lambdas for all lambda in P. And then there is also dual canonical basis here, or the upper global crystal basis in the sense of Lustig and Kashivara. So this is labeled by the same set of partitions and will be denoted L lambda. And under pi, it gets denoted onto the dual canonical basis here. But of course, again, some of the elements, now the situation is nicer because just wrong elements are going to be killed. And the elements which survive will form a basis here. So it's a nicer basis than this one. And so it behaves nicer under this homomorphism pi. So the images of these L lambdas, I will denote them D lambdas. But sometimes this L lambda goes to 0. And it's known precisely when L lambda does not go to 0. It's precisely when partition lambda is irrestricted. And it goes to 0 otherwise. And remember that partition is irrestricted if the difference between parts is less than E. And so these D lambdas for irrestricted partitions lambda will form a basis here, which is precisely a dual canonical basis of V of lambda 0. The way we set things up, that's what happens. Okay, so this is all the Lie theory I need for the moment. And now let me talk about Hecke algebras. So I will fix a field F, an arbitrary field, maybe algebraically closed, to be on the safe side. And I will fix a parameter psi, which is a non-zero parameter. This is what's usually called Q in the Hecke algebra, but of course Q is taken, so I have to use another letter. And this psi is allowed to be 1. And then HD is the Hecke algebra of the symmetric group over F with parameter psi. So it has generators T1 through TD minus 1, subject to relations TR squared is equal to psi minus 1 TR plus psi plus braid relations. So if psi is 1, which is allowed, then this is just the group algebra of the symmetric group. Psi could also be a root of unity. It could also be a root of unity in a field of positive characteristics, so you're allowed mixed situations. So we don't care. It doesn't matter for now. And so I'm also going to denote by E something which I want to be characteristic of the ground field if characteristic is positive and psi is 1, and something which I want to be the order of the root of unity if, say, field is complex field and this is root of unity. So the right definition is the minimum overall of all numbers m such that 1 plus psi squared plus and so on plus psi to the m minus 1 is equal to 0 in our field. If such number exists, and then 0 if no such m exists. But we will mainly ignore this case because, like I said, this case is going to be sort of too trivial somehow for what we want to do. And observe that if psi is 1, this is really just the characteristic of the ground field. And if psi is not 1, by multiplying with psi minus 1, you will see that you get you'll get the cyclotomic condition. So this will be precisely the order of the root of unity. And so this E sort of plays the role of characteristic, and it's going to be precisely this E under the connections with Lie algebras. So the first result which I'm going to present is going to be not quite a theorem, because I won't tell you, I will skip a lot, but anyway, I'll call it a theorem. This is our joint result with John Brandon. And somehow this is, historically, this is the last connection between these Hecke algebras and these Lie algebras. But logically, it should be the first. And so the result says that this Hecke algebra HD is isomorphic to, explicitly isomorphic to, the what's called Khovanov-Lauda-Rukia algebra of rank D corresponding to this root system. Okay, so I'll tell you a little bit more about it, but not too much. So this is Khovanov-Lauda-Rukia algebra of type gamma. So this is an algebra which is given abstractly by generators and relations. And so all this result says is that there are certain explicitly written down, and this is one thing which I'm not going to tell you, there are certain explicitly written down generators which generate the algebra HD subject only to the explicitly written down relations, which I'm also not going to tell you. Okay, but I'm going to tell you a little bit. There are some names for those things. I used to write it on the board, but somehow it didn't make anybody happier. So, and it takes time. So for 50 minutes talk, it's not appropriate. So, and I think maybe Monica will write them down. So whether it will make anybody happy or not. So, but this is a thing which is given by generators and relations in an abstract way, and the generators are as follows. There are certain idempotents E of I labeled by the tuples, by the D tuples of vertices in the Dynkin graph. So it's explicitly Lie theoretic thing. And this Lie theoretic type I want to observe has absolutely nothing to do with the type of this Hecke algebra as a Hecke algebra for Coxeter group. It's even a fluke that they are somehow both type A. You know, this type A has nothing to do. This is type A D minus 1. This type A is A E minus 1 upper 1. So this type A has to do everything with characteristic, while this type A is kind of irrelevant in some sense. So in fact, philosophically speaking, when you think about Khovanov-Lauda algebras in type gamma, you should think about this as representation theory of symmetric group SD in characteristic gamma. So for example, you can represent your symmetric group SD in characteristic E8 or E9 or E10. And that's really the right analogy for you. Or in this case, when you're doing characteristic AE minus 1, upper 1, that happens to be the real characteristic E. But so don't think that this Lie type somehow has much to do with that Lie type. It's a completely wrong idea. Okay, so generators are E of I, where I run in I to the D. And then there are certain, it's not going to be terribly helpful, Y1 through YD, and psi 1 through psi D minus 1. And there are some remarkable relations. Which, you know, I can show you if you want, or you will see them in Monica's talk. But I mean, let me draw your attention just to one thing is, for example, these relations, they're remarkable in many respects, and I don't have time to comment on that today. But for example, they don't involve psi, the parameter of Lie algebra, the parameter of Hecke algebra. So these relations are written over integers. In fact, only plus minus 1 appears as a coefficient, which is truly remarkable in a sense. Okay, so this is my first sort of almost a theorem, except that I didn't tell you, I didn't spell out the relations explicitly. Now, one of the remarkable features of this presentation is that all relations are homogeneous with respect to the following assignment of degrees. So I didn't tell you what relations are, but at least I gave you the names of the generators. And what we are going to do is we are going to assign degrees to the generators. These E of i's, which I mentioned, they are idempotents. Actually, they are mutually orthogonal idempotents which sum to identity. But some of them could be 0. So these generators E of I, because they're idempotents, they will have to have degree 0. And then we are going to assign degree 2 to every y. And then the degree of psi r times the idempotent is going to be precisely the matrix entry in the Cartan matrix corresponding to the Lie type gamma, corresponding to the Dentine diagram, with a minus in front. So it's minus ai r plus 1, where the tuple I has entries I1 through ID. Okay, so remember those are vertices of the Dentine diagram. So this Cartan matrix entry is well defined, and so we have right to do this. It makes sense. And then another remarkable fact is that if you check all the relations which I didn't write down, then the degree of the left-hand side is equal to the degree of the right-hand side. And therefore, these assignments define a Z grading on the Hecke algebra. Therefore, we get a Z grading on the Hecke algebra HD. And this Z grading is impossible to see in terms of the original Cox representation. In fact, it's very well hidden, because these relations are very different from the original ones, and the formulas for these generators in terms of the original generators are quite horrible. But at any rate, so we get this Z grading on the algebra, and so what we want to do is we want to consider graded representation theory. Z-graded modules. And in doing so, we are not going to lose any information, because by general nonsense, if you have a finite dimensional Z-graded algebra, then any irreducible module over it is automatically Z-gradable. And so you are going to do the same irreducible modules. In fact, this Z-grading is unique up to a grading shift, up to degree shift. But you are going to get more information, because you are going to look into this grading. And so now we are going to do what people always do in this situation. We are going to consider the Grothendieck groups of all the Hecke algebras taken together. And then we are going to try to consider enough functors between those Grothendieck groups, which are going to be some sort of induction and restriction refined functors. And if we collect enough of those functors, then somehow the situation gets rigid. And when we pass to the Grothendieck group, we get a module which becomes an irreducible module. In this case, module V of lambda 0. And then we fly. Okay, so let's try to do this. In fact, in this setup, it's extremely convenient to do this. It's somehow, even if you don't care about grading, I would say it's rather more convenient in terms of this Havana-Flauda picture. And here's one reason for doing this. The point is that these Havana-Flauda generators are very well suitable for the block decomposition. And the reason for that is the following, that if I fix alpha in Q plus, remember this is a linear combination non-negative with non-negative coefficients of simple roots, then corresponding to this alpha, I can define an orbit of the symmetric group which acts on the tuples by place permutations. And this orbit precisely consists of all tuples in I to the d, such that alpha I1 plus alpha I2 plus alpha ID is equal to alpha. And you can see, if you think about it, it's a sneaky way to write down the orbit of symmetric group acting on the d tuples. And then, if I define E alpha to be the sum of all idempotents which belong to this orbit, and then it turns out that this is a primitive central idempotent. Or it could be 0, because I mentioned that sometimes these idempotents are 0. So this is a little fact. that this is a primitive central idempotent O0. Okay, and so if I define now H alpha to be the HD times this primitive central idempotent E alpha, then this is a block, O0. And then if I want to consider the direct sum of all my HDs, instead I can just consider the direct sum of all H alphas over all alpha in Q plus, direct sum of all blocks. So I get this finest stratification from the beginning. And so what I want to do is I want to consider this algebra H, which is the direct sum of all H alphas, or alpha in Q plus. And if you want, this is the same, of course, as the direct sum over all d greater than or equal to 0 of HDs, because HD decomposes into those H alphas. But this is somehow more natural, except that you just have to remember that some of those H alphas are 0. And then what we want to do is we want to consider the Grothendieck groups of finite dimensional graded H modules. So if you want, this is just a direct sum over all alpha in Q plus of the Grothendieck groups of finite dimensional graded H alpha modules. Yes?
So then your H alpha is the sum over D of H alpha?
No, H alpha is a block of an individual, H alpha is a block of an individual HD. So if I take sum of all HDs, it's the same as taking sums of all H alphas. If you know which alpha belongs to this HD, it's just the one for which the height of alpha is equal to D. So, okay, so this you can stratify like this, or you can stratify more finely like that. It's a more fine stratification. Is that okay? Okay, so this I will not ever write the word graded, but when I write mod, I always mean graded modules. And then I also want to consider projective modules. Again, graded projective modules. And this is, again, the same thing. Okay, so these are the categories I want to work with. But now, of course, for standard reasons, observe that if I was just doing usual Grothendieck groups, they would be just Z modules. But because I'm doing Grothendieck groups of graded representations, they are ZQQ inverse modules. Free ZQQ inverse modules. It's because Q corresponds to the grading shift of a module by 1 up. Or Q to the n is grading shift by n. So Q appears as follows. If I want to multiply a class of a module by Q to the n, it's the same as the class of a module shifted with degree shifted by n. That's the role of Q. Okay, so I've got these Grothendieck groups, which are ZQQ inverse modules. And then I want functors, exact functors on the module categories, which will be transported into the linear operators on the Grothendieck groups. And so, so there are natural functors, which are very easy to define, which are called EI, FI, and KI plus minus 1. And you can guess why I used this notation. And so this functor, I just realized that I don't have notation for this functor, but I'll write it down and then I'll give you the missing notation. This functor is obtained by, so this is just restriction. Well, I'll write it down and then explain. And the thing is, I really want to tell you first where this functor is. So there is a natural sort of restriction functor which goes from H alpha plus alpha I block to the H alpha block. And this functor is literally just multiplying with an idempotent. You can see that this is all this thing is. And I just need to explain you how this is a module over H alpha, but it is in a very natural way, because H alpha is well, in general, not a subalgebra, but there is a natural homomorphism from H alpha to this algebra. And you will guess that as soon as I tell you what the idempotent is. Okay, so I claim that there is a natural algebra homomorphism, although not unital algebra homomorphism, from H alpha to H alpha plus alpha I, for any alpha and any I. And what you do is you just send psi to psi, y to y, and then the idempotent I of j will go to the sum the idempotent E of j will just go to the idempotent E of j concatenation add I to the last position. You see, here I should have tuples of size 1 larger than here, because the height of this is 1 more. So whenever I have a tuple here, I add I to the end of this tuple, and I get a tuple there. Okay, so that's what happens. And then you can observe that identity under this homomorphism will not go to identity, but will go to the sum. Because identity is the sum of this, it will go to the sum of all j and I to the alpha of all those ej concatenation I, which is not an identity here. And this is precisely what I call E alpha alpha I. This is the image of identity under this homomorphism. And now there is this functor because there is an obvious action of this on that. Okay? And then if I is certain adjoint functor, which I won't write down, but it's sort of H alpha plus alpha I, E alpha alpha I, tensor over H alpha comma blank. And it goes in the opposite direction. And the reason I'm not writing it down, because I'm lying slightly, there is also actually a degree shift, which you have to put in artificially, otherwise it will not be adjoint. And I'm just going to sweep it under the rug, it doesn't matter. And then there are ki's. Again, it's not very important, but these are going to be from H alpha mod to itself. And it's just certain degree shift functor. So V will go to V degree shifted by, this is plus minus 1, so it will be plus minus lambda 0 minus alpha alpha I check, if you want. So this is even a precise definition. Okay, so then as you consider the corresponding, these functors are exact, so you can consider the corresponding classes of these functors, which will be linear operators on these Grothendieck groups. So these Grothendieck groups will become or rather these functors will yield linear operators acting on these Grothendieck groups. And then you can ask the usual question, which of course has been considered a lot in the ungraded situation. What do they generate and what kind of module you get? And so the first theorem, which we proved with Brandon, is as follows, that this module can be identified because the linear operators, which I just defined, EI, FI, and KI plus minus 1, or rather, yeah, I'll call this KI plus minus 1. I'll call this EI, and I'll call this FI. And these were supposed to be script. So now these linear operators, defined representation theoretically, satisfy quantum Serre relations for the type A, for a affine type A algebra UQ of G, which we have introduced. And therefore, we obtain a module action, we obtain a module structure over UQ of G on these Grothendieck groups. Now, you have to be a little bit careful because these Grothendieck groups are defined over ZQQ inverse. And when I talk about module, I better extend scalars to the field. So let me do that. And so, okay, so but what I want to say is that when we extend scalars to the field, you get a module which is identifiable, and this is precisely v of lambda 0. So let me do that. So this h mod, and now I will extend scalars to q of q. And then it doesn't matter whether you worked with h mod or h proch, because when you extend scalars, you get the same vector space. And so this becomes a uq of g module. And this module can be identified, which is part 2. So there is a unique isomorphism of uq of g modules which is between these Grothendieck groups modules and the module v of lambda 0. Such that you can take the trivial module over the algebra H0. Remember, I have H alpha here for any alpha. So H0 is a trivial algebra which is a copy of the field. And so it has only one irreducible module, which is a copy of the field. And so this class under this isomorphism goes to the highest weight vector V+. And then everything else is uniquely determined. And so there is a unique isomorphism between this representation theoretically defined Grothendieck group and this module. So I will refer to this isomorphism as categorification isomorphism. So call it categorification isomorphism. And finally, under this isomorphism, it's really very convenient to have H alphas from the very beginning. Because, of course, H alphas are natural direct summands in here. And they should correspond to some natural direct summands in there, which are weight spaces. And it turns out that they do. So under the categorification isomorphism, this H alpha mod, which is a natural direct summand here, gets identified with the weight space of this module, which is precisely lambda 0 minus alpha. So this is very convenient notation. Is okay? Now what I want to say is, remark is that, of course, remember that my whole, so my color chalk presentation was designed to convince you that the only goal of this talk is to explain that if you want Q on the left, on the right, then you want to add the word graded on the left. And using this, you can quantize all the known results. And so this is quantization of very well-known results. I think Lascaux, Leclerc, Thibon were the first to obtain the classical analog of this. So, and so I just write it down. So this is a Q analog, or graded analog, as you like, of a theorem by Lascaux, Leclerc, Thibon. Of a theorem by Lascaux, Leclerc, Thibon. Okay, so then now our second theorem goes further along these lines. So remember that what we did here was we extended scalars, but we didn't have to. If we don't extend scalars, we'll have these ZQQ inverse forms. And we know that when we extend scalars, we get module V of lambda 0. But if we don't extend scalars, we get some forms of this module, and these forms can be identified too. And so that's what the next result is about. So if we don't extend scalars and consider instead H proch, so this is ZQQ inverse form, then under the categorification isomorphism, which I will just shortly write as CI, it's some lattice, it's some form. And so it turns out that this is a standard lattice. V of lambda 0, ZQQ inverse, which is called Chevalier constant elastic Tietz form, depending on whom you want to please. And so it's obtained by taking the Lustig Z form, by taking the Lustig form and multiplying highest weight vector V plus by this Z form. So it will give you a Z form of the module. And on the other hand, if you consider H mod, you'll get the dual lattice or costandard lattice with respect to the Shapovalov form. So you will get identification with the costandard lattice. And then in here there is an HL pairing, which comes from the Cartan pairing on projective modules, where you take a class of projective module P and you take a class of projective module Q, and you want to define a pairing. And by definition, this is a dimension of the home space between the two projective modules, or H. But of course, now we are considering graded situation, so we are considering all homomorphisms. Maybe I should denote it by capital hom to emphasize that we are considering not just the graded isomorphisms, not just the graded homomorphisms, and this dimension should be a Q dimension, a graded dimension. So that gives you a ZQQ inverse element. And so in here you have this naturally defined representation theoretic form, and what it would be on the other side? Of course, it could be nothing but Shapovalov form of the module. And that's the result that this form under the categorification isomorphism corresponds to the Shapovalov form in here. And again, this is nothing but a Q analog of a known result. In this case, I think it was first obtained by Grainovsky. So this is a Q analog of a Grainovsky result. Okay. So the next result is not a Q analog of anybody, because if Q equals 1, the next result doesn't make sense. So what we want to do next, we want to identify a bar involution on this module. And of course, bar involution Q equals 1 is identity. So there is nothing to identify. But if you consider the quantum situation, then bar involution is extremely important. And of course, it should satisfy something natural to something, should correspond to something natural on the representation theory side. And what could it be? It could be only some sort of duality, but it should be a graded duality. Usual duality is not a homogeneous one. But there is a graded duality, which is very easy to define. And what you do is you can consider an anti-isomorphism, an anti-involution on H alpha, which is identity on generators, on the Khovanov-Lauda generators, if you want. And then you can look at the relations and see that this is homogeneous map. And once you have an anti-involution, you have an operation of duality on the module category. And then theorem 3 is that under the categorification isomorphism, so this leads to a duality, which I cannot call star because star is the usual duality. So I will call it star like that. And so the star duality, or homogeneous duality, it corresponds precisely to the bar involution. Yes, but I didn't define R alpha, but it is isomorphic to R alpha, as you know it. It's a block. Okay, so then next thing which I want to mention is that, somehow in order to move in the direction of canonical basis, we want elements which are bar invariant. And so to get bar invariant elements, corresponds to getting self-dual modules in the sense of star duality, and irreducible modules are such, provided you choose an appropriate shift. And this is a purely formal observation which was first made by Khovanov and Lauda, that if you take an irreducible module D, then, okay, so it's gradable, but there are many gradings up to a shift. But they observe that there is one symmetric one, so that when you take the dual module, you get the same module. And so there is this unique symmetric choice of the grading on D, so that D star is isomorphic to D. And so we are always going to make one. Okay, okay, so, but you see, the thing is that if you really want to get hold of D's in representation theory, we usually try to approach them through decomposition matrices. So we are trying to approximate them with Specht modules, and then D's arise as the heads of Specht modules. But the situation with Specht modules is not so easy. I mean, generally we know that corresponding to every E-restricted lambda, there is an irreducible module, D lambda, and it is obtained as a simple head of the Specht module S lambda. But there is no general nonsense result which will tell you that Specht module should be gradable. Irreducible modules are gradable by general nonsense. But Specht modules are not, because they're not irreducible, and so, not every module is gradable. So in fact, it's what you have to do is you have to grade them by hand, or by anything else, but you have to explicitly construct a grading on S of lambda as a module over our graded algebra, and then you want to do it, of course, in such a way that this map is homogeneous. And so my next theorem is joined with Brandon and Wei-Chan Wang, and it says that S lambda can be graded uniquely as a module, not just as a vector space, so that this natural surjection is homogeneous. Remember, here we fixed already a unique grading, the symmetric one. For all lambda, for all E-restricted lambda. Okay, and therefore, there are indeed classes in the Grothendieck group, in the graded Grothendieck group, corresponding to this module S lambda. And then the next question is, what are they?
So D lambda is symmetric in the grading. That's part of the same form.
Yes. So under the categorification isomorphism, if I take the class of S lambda, then it corresponds to precisely vectors which are called S lambda, the standard spanning set for any lambda. And so this is again a Q analog of a well-known result of Vascular-Thibon, I think, but I think it was known before that. It's just that the action on the Fock space is the same as the branching rule for Specht module. So this is sort of an obvious result. It shouldn't even be called a theorem unless you do it gradedly. But gradedly, it's surprisingly large amount of work. And the work goes into this, and then you need to do the graded branching rules. And if you do the graded branching rules and you look at the shifts with which Specht modules appear under restriction, you will discover those formulas for the Fock space which I don't have written down. Yes?
So the left-hand side theorem is for the E-restricted, and the right-hand side is for all.
Yes.
Is it?
You grade all Specht modules, really.
Okay. But it's not any harder to do grading.
It's not any harder. I mean, in general, Specht module is a combinatorial thing for which you have a basis. Basis which you know doesn't work. It's not homogeneous. Then you have to come up with another basis, which is very, very interesting. And this I wonder what the graded characters are for these guys. It should be some sort of, there should be some sort of graded hook formula But it's not anything anybody knows, because this Hooke formula depends on E. So there are many Hooke formulas there, one for each characteristic E somehow, even though this Specht model is free, characteristic free, but this grading does depend on the characteristic. It's a very interesting thing from combinatorial point of view, I think. I would be surprised if it was anything really new combinatorially, but who knows? I don't think anybody quite knows the answer of people I asked. So anyway, there is just one more theorem which I want to explain, and this is the analog of Hecke's famous theorem. And so in case of Hecke, we of course have to assume that we work in characteristic 0 at a root of unity, which is crucial. So far it wasn't important. Everything went through for any situation. But now we have to assume that characteristic of the ground field is 0. Then for any E-restricted partition lambda, the class of D of lambda is precisely what I call D lambda, the dual canonical basis element. And so in particular, if you define decomposition numbers in an obvious way as multiplicities of D's in S's, except that now we are doing graded representation theory, so we'll have graded decomposition numbers defined in an obvious way, D with which shift appears in S. And so that will give you a decomposition number as a polynomial. And so if you define this S of lambda over D of mu sub q as a graded decomposition number, so this of course can be found as the D mu coefficient of S lambda, but this thing is computable, for example, by Lascaux-Leclerc-Thibon algorithm. And so Lascaux-Leclerc-Thibon algorithm, which provides polynomials, now provides us with the graded decomposition numbers for the Hecke algebras. So before we would evaluate this polynomial at 1 to say that this is a decomposition number, and that's what the Hecke theorem tells us. But now you don't have to evaluate at 1. They are just interpreted as these Q decomposition numbers. And so remark is that this is a Q analog of Hecke's theorem. And I want to point out that Hecke's theorem is used in the proof of this. Okay, so we sort of try to quantize both parts, starting from the known results at q equals to 1, so to say, the ungraded situation. We are trying to grade on one side and quantize on the other. So everywhere we are allowed to use the known results at q equals to 1 and sort of try to lift them up. Yeah, I guess I'm done.
Before